Hey everybody. So, welcome to yet another demo lecture. I've got a brand new Jupyter notebook for you that's going to teach you a little bit about how to do these metrics for classification that we've been chatting about in the last lecture. So, fundamentally, when we build classifiers, we're going to care about more than just how many we get wrong. We can get things wrong by calling things that are negative class positives and calling things that are positives a negative. And those kinds of errors are systematically different, and we're very likely, in most applications, to care deeply that one of those may, for instance, be much more important than the other. So to address this problem, there are a variety of ways that we can measure the classifier's error on any set, whether it be training set or test set. So we're going to walk through that today and take a look at that in the context of sklearn. So we're going to start off with a slightly different thing since we are doing classification now. With scikit, I'm going to import a data set that is trying to call whether a particular kind of biopsy comes from a benign cancer or a malignant breast cancer. So what happens is that these cell samples are plated out and put under a microscope, and there's a bunch of different measurements that are made of the images. They look at the nuclei of the dozens or hundreds of cells that are there in the microscope slide, and they take measurements of those nuclei, how big they are, what their shape is, etc. And those become features, those measurements in the image become features in this data. So we measure like the mean area of a cell's nucleus and the standard error of the cell's nucleus, and various other things become statistics that become features in our data. All right, so we have 569 biopsy samples. Let's load them up. Okay, so here we have a nice way to both load the data and use the magic of pandas to take a look at the variables we're getting. Okay. Always, when you do any kind of machine learning, you probably want to start by looking at the data in a fairly raw form. Those of you who have taken COGS 109 or COGS 9, you know, right? The first task with data is get your hands dirty, see it as raw as you can so you can understand some of the problems you might be encountering. Okay, so what are some things we can note here? We can note that these variables look normal-like, maybe skew normal. A couple of them probably are exponentially distributed. So if we were going to do something that cared, if we're going to use a technique that cared deeply about normal distributions, we're probably okay with this data. We could probably do that, at least with some transformations to make the data more normal. But we're going to be applying today, we're going to use a decision stump. And a decision stump cares nothing about the distribution of the data, so we don't really have to worry at all. Oh, before I go any further, we should also visualize the classes, right? So this is a count up of how many of these 569 samples are malignant and how many are benign. As you can see, we've got a slight imbalance. There are more of the benign, but it's not even a factor of 2. So generally, I wouldn't worry too much about that kind of a class imbalance. Most algorithms won't really blink at that. If it's a factor of 10 or a factor of 100 or worse, okay, then you probably have to put some thought into the fact that your algorithm may learn to just call everything benign if there's 1,000 times more benign samples than malignant samples. Okay. So we've taken a look at our data. We think it's probably pretty suitable for most algorithms you might want to try. And in fact, this data set has a reputation for being super easy to classify. So we're setting you up for success here. And because we know it's such an easy task, let's use a pretty dumb classifier, in part because it's the only classifier we've really told you about from start to finish that you could implement right now, or I should hope that you could at least describe for me how a decision stump works, right? So I will stop here and let you ask yourself, what is a decision stump? How does it work? Do I remember this? Okay, I'm stopping there. So for those of you who have not either instantly recalled this or you had to think about it and you're confused, a decision stump just looks through all of these 30 variables. And it's going to choose variable 0, and it's going to go whoop, whoop, and set a threshold moving back and forth across that variable until it finds the place which the algorithm does the best. And it's going to keep track of how good it did for variable 0. And it's going to go to variable 1. And it's going to do the same thing, moving back and forth across that variable and looking for a metric that tells it how good it's doing. So there's some details about the metric, which are here inside the notebook. I encourage you to take a look at them, but for the sake of time in this video, I'm going to skip it, okay? So we keep doing that exhaustive search process with the decision stump until we find the best variable out of the 30 and the exact threshold for classifying things the best. Okay? And you should ask yourself, do we care about the format of the data with a decision stump? And the answer is no, we don't, right? We don't care about things like the fact that when you look, where is our variable here? That the worst perimeter variable is up in the hundreds, or the worst area is in the thousands, right? Whereas things like mean smoothness are down in the 100ths. So there's 5 orders of magnitude there, right? And many classifiers, 5 orders of magnitude between the different variables, you know, they might choose to care more about the big variables if you're doing something else. And it might ignore the order of those 5 order of magnitude lower variables. But decision stumps are not that way, because we're treating each variable completely individually. Each one, we find the threshold that's unique to that variable, and we don't care about one variable in comparison to another because we're working one variable at a time. So a decision stump, of all things, is about the only thing we could have chosen where we don't need to deal with the fact that the variables are such different orders of magnitude. All right, well, we're going to do some training. So we need a training set. Out of those 569 samples, we need to put aside some chunk of them for testing and use the rest for training. So we're going to start with 1/3 of the data for testing. And in sklearn, once you have a decision stump, well, it's super, super easy. Actually, before I do this, I better make sure I executed this. Yeah, I didn't. All right, so let's load up our decision stump first. Very important. Split our data, and then we can go ahead and fit the training set, right? And in the process, not only did we fit the training set, but we also got our predictions for both the training set and the test set, so we can compare those to the true values. All right, so let's take a look at our fit decision stump. This is a handy little function here, plot tree, which can help with that problem. It's going to show you that what we're doing with our stump is we're using the variable 7, and we're splitting on the threshold of 0.051. Variable 7 is, what is it? It's the, oh, I forget. I guess it's 0, 1, 2, 3, 4, 5, 6, 7. So it's the mean concave points. It's the mean number of, I believe that this measurement is, because I haven't read the paper, is, you know, how many dimples there are in a nucleus on average. Okay, so apparently that's good for making the decision because it takes our data, which we had originally in the training set 381 samples, as you can see right here, and they were 145 class 0, which is benign, and 236 class 1, which is malignant. Okay, after the split, then we get the malignant overwhelmingly in this left branch of the tree. Right, we got 221 malignants to 12 benigns, and on the right branch of the tree, we get largely benigns, 133 benigns, and 15 misclassified malignants. Okay, so we have performed classification, and it looks pretty decent overall. So when you look right here at these values we were just looking at about where you end up in the branches and the leaves of this decision stump, right? You can see that most of the answers are correct answers when you pick the leftmost branch as malignant and the rightmost branch as benign, right? But let's see, we might want to do this with a classifier that doesn't have a lovely little tree like this, right? Which tells you this confusion matrix. So you might want to actually plot the confusion matrix yourself for some other kind of classifier that doesn't give it to you. So these are the methods here which you can use to generate the confusion matrix. You can either make a nice graph, or you can just go ahead and throw out the numbers as a matrix. Okay, so confusion matrix generates these numbers right here, and plot confusion matrix shows you this lovely blue-yellow graph. Now you'll note that the numbers 133.12, right, match up with 133 and 12, and 221.15 match up with 221 and 15, right? And you interpret these as the fact that we have true positives on the top left, true negatives on the bottom right. Now, other way around. True positives on the bottom right, true negatives on the top left, and over here we have the false positives as 12 and the false negatives as 15. Okay, so lovely. We might want to look at some metrics with our train classifier. So not just the confusion matrix, which shows you the various kinds of mistakes in a table sort of fashion, but there's other ways to measure things as single numbers, right? As numbers that give you a feel for what's going on in different ways. We've talked a lot about misclassification error, and that is in sklearn implemented with the name of 0-1 loss, because it's a 0 if you're right and it's a 1 loss if you're wrong. So that's misclassification error, is 0-1 loss. The accuracy score is just the inverse of that number. It's 1 minus the misclassification error. So they're equivalent numbers representing the same phenomena differently. Now, precision and recall are two numbers which you will see a lot of. So precision is the number of true positives over all the positives that we predicted. So if we have any false negatives, right, they are going to be added to the true positives. So what we're doing here is we're looking at the true positives here, right? Plus, we're gonna put the true positives on the numerator, and this entire column, the true positives plus the false negatives, is in the denominator. So when we make almost no false negatives, then we are going to end up with a high precision. Nope, I said that exactly wrong. Jiminy Christmas. Right. True positives plus false negatives. That is right. But in this case, the thing I said wrong is that true positives are still the 221, but the false negatives are the ones we predicted as 0, but they're actually 1. That's the 15. So it's the numerator is still here in yellow, but the denominator is this whole row, the entire row. Okay? I believe that is correct. When I am wrong, I expect Piazza to jump in on me. Okay? Great. As you can see, this stuff continues to be confusing, and it's okay to have to go double check yourself with some sort of resource. All right, so there we go. We want to calculate precision. Recall is next, right? Oh, good lordy. So recall is the vertical, right? It's the true positives over normalized over everything that was actually positive. No, did I just do that all wrong? Ah! Okay. Recall is over all actually positive cases. So recall is normalized against the row. Precision is normalized. I was right the first dang time. Thank you, 11:40 at night. Right? So true positives are normalized against all predicted positives. So precision was indeed, as I said it the very first time, normalized against the column. And recall is normalized against the rows. And all that's wrong if I didn't actually type this in right a few hours ago. So, we will see. I expect Piazza will have some comments on my performance regardless. Great. So lastly, the area under the receiver operating characteristics curve is one number that represents kind of how good is this classifier at trading off between making false positives and false negatives. Classifiers that don't really have to do much of a trade-off, that can do great and have very few false positives and very few false negatives no matter what, those classifiers are going to have a ROC-OC at close to 1. It's going to get a great performing algorithm. If the classifier does basically, it just flips a coin and it guesses at chance level, the ROC-OC is going to be close to 1/2. Now, I hear you asking, what exactly is the receiver operating characteristics curve? I know you covered it in the previous lecture, but I was confused. Well, do not fear. We're going to get to that in a minute. But right now, I just wanted to let you know that instead of drawing the ROC curve, some people sometimes are going to collect data on just the total area underneath that curve and use the total area with the idea that more area is a better classifier. It's going to use that area as a stand-in for not looking at the wiggly lines of the curve. But as usual, when you use one metric instead of looking at a more complicated thing, you're losing information. There are wiggles in the ROC curve that could tell you something important about your classifier and this task. All right? But when you're dealing with gazillions of classifiers, maybe you just look at the rock-awk and use that to look at the differences between the classifiers in a 30,000 foot view. Okay? All right. Here is a quick and easy way to try out all these metrics at once. Remember, we've already trained up our classifier, our decision stump, and we've seen its predictions in both the training set and the test set. So we can just feed in a metric to this already known predictions. Okay, so we're going to get training set over here, test set over here for the misclassification error, the accuracy score, which is just the inverse of the misclassification error, precision, recall, and rock-awk. All right, some things to just kind of orient you here, right? The test set error is a little bit worse than the training set error, and we pretty much expect that, right? That's going to be the most common case, that we've probably learned a few features in the training set by memorization, or we've overfit to some noise or something like that. And the test set will feature a different kind of systematic noise. So we'll probably do worse on average. And you'll see that across these things, right? So more mistakes, 11% mistakes in the test set versus 7% mistakes in the training set. Okay, so precision and recall, remember, are measuring how precise your calls are, right? So how many true positives you get out of all the predicted positives. So if your labels include too many false negatives, your precision is going down because you're not picking the right stuff, right? The recall score is, again, your true positives over all the ones that are actually positive, right? So when you perfectly recall all the right answers, you have a high recall score. When you grab all the positives and note them as positive correctly. Okay? So we can see here is that, once again, in test set, we're a little bit worse than in training set. But interestingly, for the recall, we have a little bit worse proportionally, right? We go from 0.95 down to 0.93, and here we drop from 0.93 down to 0.89, so that's a bigger proportional drop. So we're doing great in both, to be honest, but the recall is just not quite as generalized as the precision score. We're losing a little bit while we generalize. Okay? And the rock-awk is quite high and also drops a smidge going into the test. So I'm going to let you puzzle over some of the rest of these about, like, what does it imply that the precision and recall are a little different? Okay? What do you think about this algorithm? Is it likely to overfit or underfit? So I'll leave that one as an exercise for the viewer. Okay, so what I want to get to now is just a little bit more about the rock curves and the precision recall curve that we haven't talked about at all. Unfortunately, a decision stump is not the right algorithm to use to do that. So we're going to grab something we're going to study in about a week's time, and we're going to use it right here, right now. So logistic regression is still a mystery to you at this point about what exactly it is and how the loss function works. We're going to cover it soon. But at this point, just think of it as a magic algorithm that you can use, which is going to draw decision boundaries. It's going to draw a linear decision boundary somewhere in the space that's going to optimize its loss function. Okay? Now, a logistic regression has a nature to it that we can use to get more interesting rock curves than we would with the decision stump. So let's take a look at it, right? We're going to load her up, train it on the same data. What's important at this point is that now a logistic regression is going to barf if you give it one variable that's 5 orders of magnitude bigger than another variable. It's not going to do well. So part of what we did to train it is that we did have to use a scalar to z-score, essentially, all the data. So each variable gets recalculated as how many standard deviations it is away from its own mean. All right? So that's something we did there, and we trained it up right here. And we can get the metrics. Okay? So, some things to note. Which classifier is doing better at this task just in general? Decision stump or logistic regression? Well, it's very clearly the logistic regression. So instead of 7 and 11% misclassification error in training and test, now we have 1 and 2%. So, big improvement. And I'm going to let you explore the rest of my questions here about the metrics all on your own. Now, as I said, the reason we got into this in the first place was that I want to introduce you to how to think about the receiver operating characteristics curve and also the precision and recall curve. And these are two very related ideas. So fundamentally, what you're looking at is the idea that any classifier has this decision boundary, whether it's a decision stump or a logistic regression. And what we're doing is we're finding out where to place this threshold to optimize the loss function, right? But you don't have to leave it there. That may be the optimal for the loss function you're fitting, but if we care about, for instance, making fewer false positives, and we're okay with accepting more false negatives in order to allow us to keep false positives to a bare minimum, right? Then we can move that classifier back and forth, all right? If we want to, like, make sure we don't make any false positives, it makes sense to make the threshold such that we are highly likely to make loads of mistakes in the negative way, calling things that are actually positive as negative, in order to make sure that we don't do anything to accidentally call negatives as positives. So that's the animation you see right here. And as you're moving back and forth on this classifier's location of the decision boundary, we are accepting more true positives, making sure we get most of our true positives in, and at the same time as we do that, we're probably, if we get more and more true positives, we're probably going to be accepting a few more false positives, right? So that's what you're seeing as we move that threshold back and forth, that creates the receiver operating characteristics curve. Now this is just the first of many different images that are animated like this in a really nice tutorial, okay? So a grad student did this a couple of years ago, and it's phenomenal at explaining the area under the curve stuff. Okay, oops, I need to make sure this is right here. There we go. Okay, so as we saw already, the way in which you can understand how the curve is generated by a moving threshold, moving that decision boundary back and forth. And I'm going to encourage you to explore this tutorial on your own. You can do that just by right-clicking on the animation. What you can see is that when a classifier is a poor classifier, when there's a lot of overlap between the two classes, you're just guessing, right? And the point that there's total overlap between those classes, this is just chance. Wherever you draw your dividing line, so I should say the dividing line right here is drawn on the 0, right? We're just leaving a constant threshold right there on the 0. And when it's hard to disambiguate the two classes, we get chance performance, and that lies right along the diagonal of the curve, right? 50% performance corresponds to being right on that slope of 1. And as stuff gets better and better, the classes are very well separated, we make very few mistakes either direction, then our rock curve goes up towards the top left side and makes this nice right angle. Okay. Now precision recall is doing exactly the same thing, where we move our classifier's threshold back and forth, or in this case, move how easy the classification is in and out, right? So these are hard to classify because they overlap strongly, and these are easy to classify because there's very little overlap in the tails, so we make very few mistakes, right? So you can see that the precision recall curve and the rock curve are analogs of each other. They convey a lot of the same information, but they focus on different aspects of the same phenomena. Okay? So as you get better and better, they both move to the outside, right? The chance performance on precision recall is just a horizontal line at 0.5. Okay, or at least that's true for binary classification with balanced tasks, like we have, roughly balanced tasks like we have with breast cancer, right? So chance performance in the precision recall curve is just a line that would go straight across at 0.5 for a balanced binary. Okay? And so as we get close to chance performance, you'll see that the line collapses towards, the curve collapses towards that line. Right. Now, precision recall does act different than area under the curve in a few aspects. And notably, this is true when there's imbalanced classes. And again, by imbalanced, I generally mean like a factor of 100 or more, not our breast cancer example, which is less than a factor of 2. Okay? So, yeah, I'm going to let you explore this the rest of the way, have some more time with it on your own, because it is worth your time to explore. Okay, but how do we generate these in scikit-learn? Well, it's pretty dang easy. You call a function, pass it a classifier, and give it some data, and it will generate for you a precision recall curve, which looks pretty good. It's pretty much up on that top right corner, right? So, and we can do the same thing with a rock curve that works exactly the same. There's a plot rock curve. Okay, and once again, this is a great rock curve, well away from chance, almost perfection itself. Okay, that's all I had for you. We've explored the metric spaces for a little bit, and there's lots more to come in the future. One thing I do want to maybe mention for you is the idea that, I guess I should have put this in the notebook, but there is a measure that we'll probably run across quite commonly called the F1 measure. And the F1 measure is the harmonic mean of precision and recall. So the same way the area under the curve, probably can do that in 16 seconds here. That was annoying. Okay, so we need F1 score. Just make sure I import that. And let me. So as I was saying, the F1 score is a summary of the entire precision recall curve in a single number, rather like the rock awk is a summary of the rock curve in a single number. And like all such things, it makes a bit of, throws away a lot of information about the wiggles in a way which is helpful. Oh God, this is so annoying. Why does it keep doing that? All right. Okay. There we go. So now we have F1 score in here, and I will very quickly update the GitHub copy of this notebook so that you all can have this in the notebook. Okay, great. So we've done it. As usual, oh, and I should put in the little Colab loading button so you all can go right from the GitHub right to Colab. Okay, thank you for sticking with me. I hope you learned something, and that maybe, if it's not clear, explore this notebook on your own and the links within it, and hopefully things will become more clear. All right, see you later. Bye.